Hello, discrete math fans. Now we're going to talk about the Boolean expression that corresponds to a circuit. And we need to talk about what we mean by a Boolean expression. Well, in logic, we use variables like p, q, and r to represent statements. And a statement can only have two truth values, true or false. And we created statement forms like p and, in parentheses, q implies not r. And they were composed of statement variables and logical connectors. Now, in honor of the famous English logician George Boole, any variable, like a statement variable or an input signal that can take only one of two values, is called a Boolean variable. An expression composed of Boolean variables and connectives like not, and or is called a Boolean expression. So let's find the Boolean expression that corresponds to the circuits shown below. Now, we're going to draw a dot when we indicate a soldering of two wires, and wires that do not cross are assumed not to touch. So in this circuit, there's a splitting of P at this point. So P gets fed in as an input into the OR gate and to the AND gate, but this intersection right here, we assume that the wires do not cross. Similarly, Q is split at this point and fed into the OR and also fed into the AND. Notice that we're using capital letters, P and Q, to represent input signals. Earlier we used lowercase p, q, and r as statement variables in our statement forms. So what we'll do is we'll trace through the circuit from left to right, indicating the output of each gate using symbols. So here we have P or Q coming out of this gate, and then here we have P and Q coming out of the AND gate. The P and Q is fed into the NOT to give us NOT P and Q. And finally, the P or Q and the NOT P and Q comes out here in one final expression. The book discusses this particular circuit. It's something called the exclusive OR. The output is going to be a 1 if and only if one of P and Q is 1. If they're both 1, then it's going to output 0. So we have three input variables, and we're just going to feed into a few gates here. We have a NOT, an AND, and another AND. And here's our solution. The Q that gets fed in turns into a NOT Q. Then the P that gets fed in will give us P and NOT Q. Those are the inputs into the AND gate. And then the output of this gate is fed into an and that's going to get ANDed with this R. And so here's our final result, P and NOT Q in parentheses, and then we have AND R. We should notice something interesting about this particular circuit. The output is 1 for exactly one combination of inputs. And that's when P is equal to 1, Q is equal to 0, and R is equal to 1. And for any other combination of inputs, we're going to get an output of 0. What we're going to say is that this circuit recognizes exactly one particular combination of inputs. The output column of the input-output table has a 1 in exactly one row and a 0 in all other rows. So we'll make a definition and say that a recognizer is a circuit that does exactly this. It outputs a 1 for exactly one particular combination of input signals and outputs zeros for all other combinations. So here's the input-output table for the recognizer that we created. It just looks like this. You should see that for this combination of inputs, P equals 1, Q equals 0, R equals 1, is the only input in which we get a 1. all the other ones, we got an output of 0. So that's what a recognizer looks like. We're going to be using recognizers as fundamental building blocks to be able to create circuits for any type of input-output table that we want to create. Okay, that's all for now.